Hi, welcome to Algebra 2 Common Core. Today in lesson number 5, we're going to take a look at some application problems that we can solve using the quadratic formula. So in the box at the top of your notes, you'll see the quadratic formula. This should be familiar by now. X is equal to the negative of b plus or minus the square root of b squared minus 4ac all over 2a. So for exercise number 1, we have the quadratic function f of x equals x squared minus 4x minus 36. In part A, it says let's algebraically determine this function's x-intercepts using the quadratic formula. So just a reminder, when we are trying to find x-intercepts for a function, that of course is going to be where f of x is equal to 0. So we're going to set our quadratic x squared minus 4x minus 36 equal to 0. Since we're going to be using the quadratic formula, I'm going to write down my values for a. So of course a is 1 because that's the coefficient of x squared. B is equal to negative 4 because that's the coefficient of x. And c is equal to negative 36 because that's my constant. So let's go ahead and substitute those values into the quadratic formula. So I would have x is equal to the negative of negative 4, which is positive 4, plus or minus the square root of b squared, so negative 4 is going to be squared, minus 4 times 1 times negative 36, all of that's under the radical, divided by 2 times a, or 2 times 1. Now go ahead and enter the radicand in your calculator and see what we get underneath the square root sign. So on my calculator I got 160 underneath the radical. So I now have x is equal to 4 plus or minus the square root of 160 over 2. We'd like to simplify this, so we're going to say x is equal to 4 plus or minus 16 is a factor of 160, and 16 is a perfect square. So when I take the square root of 16, the 4 comes outside the radical. But then 10 goes underneath the radical because 10 times 16 is 160, but 10 doesn't have any perfect square factors. And then we'll divide both parts by 2. So this gives me as my solution 2 plus or minus 2 radical 10. Now I see that these two solutions, first of all, are conjugates of each other. We were introduced to that in the last lesson. Conjugates just means that I have the same two terms. In one case, the two terms are being added together. In the other case, the two terms are being subtracted. Now because I've got a square root of 10 in my answer, that tells me that I've got irrational roots. So the best that I can do is get a decimal approximation of those roots. So in part B it says, let's express those x-intercepts correct to the nearest hundredth. So if I go to my calculator and I enter 2 plus 2 radical 10, so go ahead and put that into your calculator, and then round your answer to the nearest hundredths. I got 8.32. Enter it in your calculator and make sure you're getting that same answer. Now take a minute to enter the other one, 2 minus 2 radical 10. Did you get negative 4.32? Now it says, let's use our calculator to sketch a graph of this. We then want to check our solutions for the x-intercepts by using the 0 command and making sure that I'm getting those zeros on my graphing calculator as well. So I'm going to turn off the video for a minute. I want you to pause it and put this function into your graphing calculator. Do the graph. Make sure you adjust your window on your graph. You can see that your x's are going to go from negative 20 to 20. I don't want to count by 1s there. I might count maybe by 5s. Also adjust your y values in your window. So I have to go from negative 50 to 50. I think I'll count by tens. Once you get this graph in your graphing calculator, then also graph it on the piece of paper in your notes. And then come back and check and see if yours looks like mine. Welcome back. Does your parabola look like mine on your graph? Notice that I identified the x-intercepts at negative 4.32, 0 and 8.32, 0. I did also check by using the 0 function on my graphing calculator to be sure that my graph crossed the x-axis at both of those points. I included a couple extra points on my graph. I said, let's go ahead and find the y-intercept for this graph. So of course, when I'm finding the y-intercept, I let x be 0. So the function value at 0, when I substituted 0 in for all of the x's, I got as my answer negative 36. So here is that y-intercept. I also found it helpful to find the vertex, and I used my graphing calculator to find that vertex. In this case, the vertex is a minimum point, so I used the second calculate minimum on my graphing calculator to find that point and then go ahead and graph it. So we can see that we can come up with a very accurate sketch of this graph, and we found the roots or the x-intercepts using the quadratic formula. So this was a really good use of our quadratic formula, and then going ahead and finding the decimal approximation for each of those roots. In exercise number 2, it says, which of the following sets represents the x-intercepts of y equals 3x squared minus 19x plus 6? Now again, we're seeing that word x-intercept. So that should be telling us that we are letting the y be equal to 0. So I'm going to make my equation 3x squared minus 19x plus 6, and I'm going to set it equal to 0. Please pause the video and solve this quadratic equation for the x-intercepts by using the quadratic formula. When you have finished, check which of your multiple choice answers make sense, and then come back and check with mine and see if we agree. Please check your work with mine. I identified that A was 3, B was negative 19, and C was 6. So when I substituted these values into the quadratic formula in simplified form, I got 19 plus or minus the square root of 289 all over 6. Now, 289 is a perfect square, so that's really helpful for us. That tells me that this time we're going to have rational roots instead of irrational roots. So rational means that I don't have a radical in my answer. Instead, my solutions are both rational numbers, which can also be written as fractions. When I simplify both of those answers, I see that I get 6 for one of the roots and 1/3 for the other one. So that's telling me that choice number 4 is the choice I'm going to make. Now let's take a look at an application problem. For example number 3, it says the Celsius temperature C of a chemical reaction increases and then decreases over time. According to the formula, C of T is equal to negative 1/2 T squared plus 8T plus 93. T represents the time in minutes. Use the quadratic formula to help determine the amount of time to the nearest tenth. So notice that we're going to have to do some rounding here. So that's telling me that I'm probably getting irrational roots this time. It takes for the reaction to reach 110 degrees Celsius. So here's my goal. Here's the value that I want my answer to be. So if I take a look at this and think about what the parabola is going to look like, it said that the function increases and then decreases. Now I don't know exactly where my axes are for this one because I haven't written it in vertex form, but I can see that with the negative in front of the t squared, that tells me that I have a parabola that faces down. So my temperature is going to increase first of all and then start decreasing. And I want to know when the temperature is going to reach 110 degrees. So at some point we're going to have a horizontal line here at 110, and we want to know where does the parabola hit that horizontal line. So we could plug this into our graphing calculator, but it says that we want to use the quadratic formula, so we could use our graphing calculator to check our answer. So we want to know when C of t, which of course is equal to negative 1/2. I'm going to replace the 1/2 with a 0.5 t squared plus 8t plus 93 is equal to our target temperature of 110. Now before I can use the quadratic formula, of course I'm going to have to write this in standard form. So let's subtract the 110 from both sides of the equation. So I would have negative 0.5 t squared plus 8 times t, and then subtracting the 110, I've got negative 17 equals 0. Well, this is a quadratic equation that clearly doesn't look like it's going to be easy to factor, if factorable at all. So I'm going to use the quadratic formula where a is equal to negative 0.5, b is equal to 8, and c is equal to negative 17. I want to make a nice equal sign there. So go ahead and substitute those values into the quadratic formula. So here you see my work in substituting a, b, and c into the quadratic formula. Use your calculator to find the value of the radicand. So I'm getting negative 8 plus or minus, works out to be the square root of 30, all over 2 times negative 1/2, which of course is negative 1. So I am going to set this up as two possible solutions for t. My first value of t is going to be negative 8 plus radical 30 divided by negative 1. And my second solution will be negative 8 minus radical 30 divided by negative 1. So stop the video for a minute. Make sure when you're plugging this into your graphing calculator, you're putting parentheses around the whole numerator and then dividing by negative 1. So come back when you have the decimal approximations and please round these to the nearest tenth. So when I found the decimal approximations, I got 2.5 minutes and 13.5 minutes. So I can clearly see that as the temperature is rising, it's going to rise, and at time 2.5, it's going to hit a temperature of 110. Then it's going to start coming back down again and again hit a temperature of 110 at 13.5 minutes. Now I also plugged this into my graphing calculator so that I could see a better picture of this graph. And as it turned out, I ended up with a graph that looks something like this, where my axes happened right about here and here. This is the spot at 2.5 when the temperature was 110, and this was the spot at 13.5, the second time that the temperature hit 110 degrees. You will have to adjust your window on your graphing calculator to fit this whole graph. I made mine go up to a maximum on my y-axis of 125 so that I could see the top of the graph. Our last application problem today is one that is going to be really useful for us when we are trying to solve systems of equations. You'll notice that for these two equations, the first one is a parabola. Y equals 6x squared plus 19x minus 15. The second one is a line. Y equals negative 12x plus 15. So we want to solve this system. I'm going to use the method of substitution. So that means that I'm going to substitute negative 12x plus 15 for this y because both of these expressions are equal to y. So I'm going to have the equation 6x squared plus 19x minus 15 is equal to negative 12x plus 15. Now, don't make the mistake of thinking that those 15s are going to cancel because on the left side I've got negative, on the right side I've got positive. We need to put this equation in standard form, so let's add 12x to both sides of the equation and also subtract 15 from both sides of the equation as well. So I have in standard form my equation 6x squared plus 31x minus 30 equals 0. And again, this is a really tough equation. It might be factorable, but those numbers are really big, so I don't want to even try to factor this. Completing the square would also be a difficult method here because I'd have to first of all divide each and every term by 6, and not all of them are divisible by 6. So I'm going to have kind of messy fractions if I were to try to complete the square. So a good way to solve this equation is by the quadratic formula. So I'm going to say a is equal to 6, b is equal to 31, and c is equal to negative 30. Substituting these into my quadratic formula, I have x is equal to the negative of 31 plus or minus the square root of 31 squared minus 4 times 6 times negative 30 all over 2 times 6, which is 12. When I substitute those numbers into my graphing calculator to evaluate the radicand, I see that I get negative 31 plus or minus the square root of 1,681 over 12. Now, as it turns out, 1,681 is a perfect square. So negative 31, I did that on my calculator. I didn't recognize that one. So negative 31 plus 41 over 12. Negative 31 minus 41 over 12. So in simplest form, I'm getting 10/12, which reduces to 5/6 for my first x value, and negative 72 over 12, which of course is negative 6 for my second x value. Now, as expected, this parabola and this line cross each other 2 times. Now don't stop with just the x-coordinates. We need to find the y-coordinates for their point of intersection. So when x is equal to 5, 6, I'm going to use the easier of the two equations to solve for the y-coordinate at the point of intersection. So I'm getting y is equal to negative 12 multiplied by 5, 6 plus 15. So that gave me as an answer 5. My point of intersection for the line and the parabola, 5, 6, comma 5. Now let's try an x value of negative 6 for our other point of intersection. Y is equal to negative 12 times negative 6 plus 15. So for this y value, I'm getting an answer of 87. Wow, that's much different. So my point of intersection, negative 6, 87. Now I'm going to go to my graphing calculator and I'm going to enter both of these equations into y equals. One in y1, the other in y2. If I want to look at the graph to tell where the points of intersection are, I'm of course going to have to switch my window here. I'm going to have to expand the window to include both of those points. So my x's, I think it's going to be big enough if I go from negative 8 to positive 8 on the x-axis. And I can count by ones. My y's don't need to be negative, so I can start at 0. But I have to get big enough to include this point 87. So if I go up to, I don't know, maybe 100 on my y-axis, I should be able to see both points of intersection. Remember that we can check on our calculator using the second calculate menu and do intersection to find both of those points of intersection and make sure that we are correct. We've had some very good work today on the quadratic formula. We'll continue this work in class the next time. Have a great night, and we'll see you next time.